Welcome to your next math lesson. All right, so we are on 9.1. Yeah, 9.1. We've made it so far. So let's go ahead and get started. And we are talking about logarithms and logarithmic functions. So I'm not sure if you've ever heard of logarithms before, but we're going to talk about them now. So we will define logarithms and we will evaluate logarithms. So they're real life example problem or situation. A skydiver uses an altimeter to observe the altitude or height above Earth's surface during a dive. As the skydiver is falling, the atmospheric pressure is increasing. The altimeter measures the atmospheric pressure and converts it to altitude. What is the mathematical question you ask? I'm going to ask how fast they're falling, but that's more of a physics thing. I'm assuming they have something to do with the altimeter. And what information would you need to answer your question? So let's see what they got. So the skydiver will open the parachute at a predetermined altitude. The function p equals 100 e to the power of a over 8 models the atmospheric pressure in kilopascals given an altitude in kilometers. So you can figure out the pressure based on your altitude. But we want to change that so that we have an altitude based on the pressure. So right now, we don't really have a mathematical mechanism to do that. I mean, maybe taking the eighth root of everything, but that's going to be kind of hard, and that's still not going to give us that a by itself. So we need a mathematical way of doing that we can then program into this little altimeter computer to figure out. So let's figure that out. In order for that altimeter to work that we just talked about, we actually need an actual mathematical algebraic way of programming it to do all that math that we want it to do. And so that is where logarithmic or logarithms and logarithmic functions come into play. Right there. So let's see here. Understand logarithmic functions as inverse of exponential functions. So basically, we have this function f of x equals bx, and so if we were to put an actual number for the base, b is the base, so then we would have f of x, and we're going to use 2 as that number. So an inverse of that would be anything that undoes the function that we use. So if we raise 2 to the x power, what would undo that x power? And that would be or at least the inverse function would be a logarithmic function. So the inverse of an exponential function is a logarithmic function. A logarithm is the exponent to which a base must be raised to produce a given number. So let's look into that. Let's put it into symbols so that it makes a little bit more sense. So a logarithm problem or equation would look like this. We use the letters log, log, and you'll notice that there's always a base as a subscript and then another number. So again, they always look like this right here. And the way that reads is f of x equals log base b of x. So the logarithm with base b of x, or log base b of x. So that's how you would say these things if you're talking about them. So as I mentioned, the logarithm is the inverse of an exponent of an exponential function. And so to remind you, an inverse of a function is where you take your inputs, this side, and your outputs, and you switch them. So in the inverse of this function, these would all be your x's, and these would be your y's. So it is the opposite or inverse of the f of x equals 2 to the power of x. So here we have a chart of just our normal f of x equals 2x, and it should be a fairly familiar exponential growth curve that we've been talking about. So if we looked at the inverses though, or the inverse, so my x's would be all these numbers, and my y's would be all these numbers. So if I were to plot that out on that same point in red, so 0.25, so 0.25 is negative 2, it's going to be down here somewhere-ish. 0.5 is negative 1, again, ish. 0 is 1. Oh wait, no, I'm sorry. X is 1, y is 0. X is 2, y is 1. X is 4, y is 2. X is 8, y is 3. So notice there's a reflection here, right? Okay, so you'll have to kind of remember this graph, or I'll just come back to it, but it's going to go along with my screens, I'm sure you've seen before. So how does a table f of x equals 2x reveal that its inverse will be a function? So in order to be a function, you have to have what's called a 1-to-1 ratio, or a 1-to-1. For every f of x, there is an answer, I guess. And so the values of the function are always positive. Well, we know that that's not the case. For each value of the function is a real number. So that's technically true, but not relevant right now. So for each value of the function, there is only one corresponding value. So that 1-to-1 ratio that I was talking about. So one way to do that, and I'm purposely leaving this up there so we can kind of see it, is using what's called the horizontal line test to see if there is an inverse function, if that would work. So like, if you had a parabola, you know, x squared, there is not an inverse function because it does not pass the horizontal line test. So yeah, the graph passes the horizontal line test. And again, the horizontal line test is if you draw a horizontal line anywhere on the graph, you would only get one point. So like this one, you would only ever intersect the graph at one point. So that's what they mean by the horizontal graph. I'm sorry, horizontal line test. Do you need to restrict the domain of f of x equals 2x for its inverse to be a function? So if we're thinking about that, are there any x values that would absolutely 100% not work? And I want to say no. Think of x equals 0. Yeah, no, that should be fine. Because it would eventually cross. Let's see here. The domain and what characteristics of f of x allows you to make this conclusion. So let's hear no. Is that the right one? I didn't think so. So no, since f of x equals 2x is always increasing, there will never be a different domain values that correspond to the same range values. So how does the symmetry of the graph? We talked that it has that inverse when I drew that line on there. That was like a y equals x line right there. So I don't want to spend too much time on this because I just think that they're getting bogged down in some of the characteristics, which are good to know, but I think that once you start working with the functions, you will pick up these characteristics and they will make more sense. So while the exponential function has an x-axis as its asymptote, the logarithmic function will have a y-axis as its asymptote. How can you use the values on table x or on tables for f of x? So you just switch the pair, reverse the domain and range values. And then, if you were looking at that chart and we were to reverse them, this is the graph that we came up with. And look, they wanted us to make a graph, we already did. Too easy, right? And the graph does help confirm some of our answers. So let's get into it. From exponential to logarithmic equations. I'm glad you asked, because that's what we're talking about. Let's see here. So again, we talked about that logarithmics are inverse functions. So here is, oh, come on, pencil. Here is one of our big kind of takeaways. So this right here is something that you need to remember. So that really needs to be committed to memory. I dare say you will have to memorize that, but you will use it so much that hopefully you'll just remember it, because you're going to use it over and over and over again in this class, in your mathematical academic career, as well as if you go into any STEM science field, things like that. So let's get it now. So basically, we have our exponential function b of x equals a. We can use all of that and return the x value. So that would look like, that's usually log is in print. So log base b of a equals x. So this would help us with that, that very first problem, because that x was in that exponent, so we could use a log base of b to figure out the altitude. So these are inverse functions. So in the same way, like f of x equals 6 plus x, so the inverse of that, actually I don't want to use an f of x, I want to use y because I think it'll be a little bit easier to do. So the inverse of that, as you all know, would be y minus 6 equals x. So notice how 6 plus x, and the inverse is y minus 6. So that's just one example of, kind of like an inverse. So they gave an example, b of x equals a, and a divided by b equals x. They are equivalent ways to express the same relationship. In the same way, b to the power of x equals a, and log base b of a equals x are equivalent ways to express the same relationship. So they can be used, I don't want to say interchangeably, but they express the same relationship between these numbers. And being able to switch between them is very helpful in dealing with different situations in our mathematical world. So let's try some things out here. Complete the following to convert 5 to the power of 3 equals 125 to a logarithmic equation. So remember, the way you say this, and this is kind of how I remember it, log base b of a. So I always remember that this is the base of the exponent. So it goes down into the subscript of the log, and then the rest of it just kind of moves around and falls into place, in my mind. You need to find your own way to remember it if mine doesn't work. So the equation states that the base 5 raised the exponent 3 gives the power 125. So that's basically what this is saying right here. So complete the following to convert 5/3 to 5 to the power of 3 equals 125 to a logarithmic equation. So again, this is saying the same relationship, or that the third power of 5 is 125. That's a really bizarre way of saying it. Nobody ever does that. This one I think is probably a little bit more useful. So this is equivalent to saying that the exponent you must apply to the base, so the base is 5, to write as a power is 3. Man, again, this is a really bizarre way of saying this. So here's what you have to actually be able to do. Take this and turn it into a log. So figure out which one goes here. So again, 5 is the base. So it is log base 5. So your options are either this one or this one. And it already equals 125. We want it to equal something different. So log base 5 of 125 equals 3. So again, don't worry too much about this stuff up here. That's a really bizarre way of saying it. This is the important part right here. So let's see here. Complete the following to convert this to a logarithmic function. So I'm just going to do it on the side here first, and then we'll plug things in. So remember, log base b, so 6/7, of t is going to equal r. I tried to erase that. For some reason it's not working, but whatever. There it goes. So the equation states that the base 6/7 raised the exponent r gives the power t. Okay, sure. Or that the rth power of 6/7 is t. Again, weird. So here we go. Again, weird wording up here. So apply to the base 6/7 to write blank as a power. To write t as a power is r. So basically we're looking for this one. So that's log base 6/7 of t equals r. So again, this is what you need to be able to do. Okay, let's try to solve some of these things. So when you're evaluating a logarithmic function, it is helpful to switch this f of x into a y, and then switch it to and from an exponent so that you can see it a little bit easier. So for example, it helps when an input is a recognizable power of a base. For example, 25 is a recognizable power of 5. So it is easy to recognize that f of x equals log base 5 of x will output 2 for an input of 25. So that would mean if x equals 25, f of x would be 2. Because it would, so if you would convert that into an exponent, 5 to the power of 2 would be 25. So it can be helpful to let y represent an output of a logarithmic function and then convert the equation to exponential form. So that's what we're going to kind of do. So this first one here, so you've got f of x equals log base 4 of x. Find f of 64 and f of 116. So in order to do this, so we can say, let's let f of 64 equal y. And then, so we've got our, let's zoom in a little bit here. So then we've got log base 4 of 64 equals y. So here we are right there. So then from there, we can switch that. So remember, to turn this into an exponent, we've got our base, log base 4. So our 4, our y comes up here, and the whole thing equals 64. So this might be a little bit easier to recognize. Okay, how many times do I have to multiply 4 together until I hit 64? So if you don't know that off the top of my head, like me, you just pull out your calculator real quick, start going 4 times 4 is 16 times 4 is 64. Hey, look at that. Or you can just look at the next line of the whatever. So then you can say 4y equals 3, y equals 3, f of 64 equals 3. So done, you got it. So now you can do the same thing with f of 1 over 16. I assume we're going to be doing that. Oh yes, let's answer questions. Blah, 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 blah. So let's do the same for f of 1 over 16. So again, we're just going to set it equal to y. And you can really use any variable you want. It doesn't matter. It doesn't have to be y. It could be z, q, elemental p. I don't care. It doesn't matter. But you're going to set it equal to y. So then you have this. Log base 4 of 1 over 16 equals y. So then when we convert that into an exponent, log base 4, and then your y turns into your exponent, equals 1 over 16. So then again, you ask the same question, how many times, so there we are, how many times do I have to multiply how many times do I have to multiply 4 together to get 1 over 16? That's when you're going to start using your negative exponents. So remember, if y is negative in this situation, that's like dividing by. So you've got like 4 divided by 4 divided by 4. What were we going for? 1 over 16? My calculator's in decimals. Divided by 4. Yeah, so what is it? So you have to use it 2 times, and so that would be a negative exponent. So you would do negative, or raise 4 to the negative second power. And then you just do some algebra, and you've got your answer right there. Right? Too easy. So using a logarithmic and logarithmic function. So if you haven't noticed already, on your calculator, there is a log and a quote-unquote natural log button. So the log that is on your calculator refers to a common logarithm, and then the ln on your calculator refers to a natural logarithm. So a common logarithm is anytime you see log just written like log of x or something like that, that insinuates log base 10 of x. So if nothing is written there, it is a quote-unquote common logarithm, and it is just a log base 10. So if you see natural log, ln, that is the same as log base e. So again, both of these buttons are on your calculator, and so we can use them to solve problems. So again, if we see the expression ln of x is read, ln of x indicates, evaluates a log with a base e. And so I'll show you that on the calculator here in just a minute. So our problem that we're going to use is the loudness L in decibels, dB, of a sound is modeled by L equals 10 log, remember that's common log, of I over I naught, where I is the sound's intensity and I naught is 10 to the negative 12, which is the approximate intensity of the softest hearable sound. So we come down here and we are asked to use the loudness model. Well, what's the question? Blah, blah, blah. Got it. Okay, so intensity of a moderate rainfall is I equals this. Intensity of close lightning strike is I equals 10 watts per meter squared. So let's see here. Shows the intensity of sound from moderate rainfall from a close lightning strike. What is the loudness in decibels of moderate rainfall? So moderate rainfall, so that's going to be our I, is going to be equal to 10 to the negative fourth. So we're just going to plug all that in, which is all right here. So we are going to have 10 log of 10 over negative 4, or 10 to the power of negative 4, over 10 to the negative 12. As you know from our last section, chapter, module, whatever, these two exponents, you can simplify that as to 10 to the negative 4th minus negative 12, which would also be 10 to the 8th. So now we have this thing right here, 10 log log of 10 to the 8th. So based on that, you can then simplify that and call this 8 because it is log base 10 of 10 to the power of 8. So how that would be, or like how to think about that is how many times does 10 have to be multiplied by itself to get this number? Well, we already have it in an exponent form, so it would take 8 times. That would be the number. So how do you use that on the calculator? We'll pull up our handy dandy calculator. So here's the log button, here's the natural log button. Remember, there's our e to the x button, there's our 10 to the x button. So if we were going to do 10 log of 10 to the 8th, so we would just go 10 times log. Notice how it has an open parentheses. So we can say 10 to the power of 8. And if you just push enter, you're going to get an answer here. But if you had any more, then you would need to close that parentheses. To be safe, I would get into the habit of closing your parentheses. It's just a good habit to have. And so we are going to have, the whole thing would equal 80, but obviously the log of 10 to the power of 8 is 8. 8 times 10 is 80. So that's how you do it on the calculator. And so we get 80. Too easy, right? So what property justifies rewriting all of this as 10 to the 8th? That would be the quotient of powers property, because this here is a quotient. Remember, that's from our last module. And log by itself is log base, that's the common log base 10 logarithm. So log of 10 to the 8th equals log base 10 of 10 to the 8th, which is 8 by definition. So there's our answer. That wasn't too bad, right? Let's do one more example. So use a logarithmic model. So radon is a radioactive gas that can accumulate in basements. The function m equals m naught times 1/2 to the power of t over 3.8 describes the mass m of radon remaining after t days from the initial amount with mass m naught. After how long will 0.5 milligrams of radon remain from the initial amount of 16 milligrams? Okay, so first things first, let's substitute everything in. So let's see here. It said after how long the initial amount of 16. So the initial amount, m naught, is 16. And we want to figure out t. T's are unknown. That brings me back to my physics days. I'd always write down what we don't know. And then m is equal to 0.5. But we need to find t. And notice t is in our exponent. So we take all this, we plug it in, and we're sitting at this part right here. So 0.5 equals 16 times 1/2 times t to the 3.8. So decimals are evil. So we switched everything over. Wait, did we? Yeah, so right here, they took care of the 16. So what had happened was we switched that 1.5 to 1 over 2 equals 16 times 1/2 to the power of t over 3.8. So we divided both sides by 16. By 16. 16 times 2 is 32 equals 1/2 t to the 3.8. So that's how they got there. Sorry, I just scratched that out real quick. So now that we are here, so 1 over 32 equals 1/2. I'm trying to write it slightly better this time. So how do we get to where we want to go? We want to get that t by itself. So we are essentially going to rewrite it using a logarithm. So remember, we've got our log part right here. So that's going to be log base 1/2 of 1 over 32 equals t over 3.8. That's what they got right there. So from there, we can multiply both sides by 3.8. So now we have 3.8 log of 1/2 1 over 32 equals t. So now t's by itself, and all of these are just numbers, so we just got to figure that out. So what the log base 1/2 means is how many times do I need to times 1/2 by itself to get 1 over 32. So that means that we can rewrite 1 over 32 as 1 over 5, 3.8 log of 1/2 over 1/2 5. So this would then all simplify to 5. And at this point I would just throw it into a calculator, but they tell us right there. So that's going to equal 19. Just to double check them, 3.8 times 5 is 19. 19 even. Neat. So why is 1 over 32 rewritten here as 1 over 2 to the power of 5? So the logarithm is an exponent to which the base must be raised to obtain the power. Since the base is 1/2, you must be able to express 1 over 32 as a power of 1/2 to identify the exponent. And there you go. Hey, so that's a wrap. That's our introduction to logs. We're going to be using logs a lot in the next couple weeks, so buckle up. Here we go.